November 18th, 1944. The fog-shrouded forests near Hürtgen, Germany. Private First Class Thomas Harmon crouched behind a shattered oak tree, his M9 bazooka resting against his shoulder, its aluminum tube cold against his cheek. Through the mist, he could hear it before he could see it, the deep mechanical rumble of a Panther tank grinding forward through the muddy forest trail, its tracks chewing through frozen earth with methodical precision. Harmon's loader, Private Jack Sullivan, knelt beside him with a rocket, waiting for the signal. They had been told that the 2.36-inch bazooka could stop any German tank. The training sergeants back at Fort Benning had been emphatic. Hit the side armor, hit the rear, hit anywhere but dead frontal, and the shaped charge warhead would burn through steel like a torch through paper. The Panther emerged from the fog at 70 yards. Harmon could see the iron crosses painted on its glacis plate, the long 75mm guns swinging left and right as the commander searched for targets. Sullivan tapped his shoulder twice. Ready. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Harmon centered the optical sight on the Panther's side armor, just below the turret ring where the instructions said the fuel tanks sat. His finger tightened on the magneto trigger. The rocket whooshed from the tube with that distinctive sound that had given American infantry hope against German armor. The smoke trail arrowed straight toward the Panther's flank. Impact. The shaped charge warhead detonated with a sharp crack against the 40mm side plate. Harmon watched through the dissipating smoke, waiting for the secondary explosion, the gout of flame that would signal a fuel tank, igniting or ammunition cooking off. The Panther kept moving. Its turret began traversing toward their position. Sullivan's voice cracked with panic. "Did we miss? We hit it square. I saw the hit." Harmon could see the blackened impact point on the Panther's side armor. A clear hit. Center mass. Perfect placement. But the tank was accelerating now, its gun barrel swinging directly toward their hiding spot. No penetration. The Panther's coaxial machine gun opened fire. 7.92mm rounds chewing through the oak tree in long bursts. Harmon and Sullivan scrambled backward into a drainage ditch as the German tank commander, satisfied that the threat had been suppressed, swung his turret forward and continued grinding deeper into American lines. That night, shivering in a foxhole 300 yards behind the front lines, Harmon tried to understand what had gone wrong. He had done everything right: proper range, proper angle, proper target area. The shaped charge warhead should have penetrated. The physics said it should have penetrated. But the Panther had shrugged off the hit like it was nothing. What Harmon didn't know, what none of the American infantry knew in the autumn of 1944, was that the bazooka's reputation as a tank killer was built on a foundation of carefully managed expectations and incomplete battlefield data. The weapon that had been rushed into production in 1942, that had been hailed as one of the war's most revolutionary innovations, was meeting an opponent it had never been properly designed to defeat. The story of how the bazooka became both America's infantry anti-tank answer and one of World War II's most oversold weapons begins not with its development, but with the science that made it theoretically possible. The shaped charge effect that powered the bazooka's warhead had been discovered decades before anyone thought to mount it on a rocket. 1888, the Naval Torpedo Station in Newport, Rhode Island. Charles Edward Munro, a chemist and explosives researcher working for the United States Navy, was conducting routine tests on high explosives when he made an observation that would eventually revolutionize anti-armor warfare. Munro was experimenting with gun cotton, a highly unstable form of nitrocellulose explosive, pressing blocks of it against steel plates to measure blast effects. During one test, Munro had carved the letters USN into a block of explosive, the letters facing the steel target plate. When he detonated the charge, he expected the letters to be obliterated by the blast. Instead, when he examined the steel plate, the letters USN were clearly impressed into the metal, as if engraved by some impossibly precise tool. The blast had somehow focused its energy along the pattern of the cavity. Munro spent the next several years investigating this phenomenon. He discovered that any cavity carved into an explosive charge would focus the detonation energy forward along the axis of the cavity. A conical hollow would produce a focused jet of explosive gases. A hemispherical depression would create a different pressure pattern. The deeper and more precisely shaped the cavity, the more pronounced the effect. He published his findings in 1890, calling it the hollow charge effect. The military implications were immediately obvious. If explosive energy could be focused and directed, it could be used to defeat armor plate that would otherwise resist blast effects. But Munro's discovery arrived at the wrong moment in military history. The 1890s saw no urgent need for anti-armor weapons. Tanks didn't exist yet. Armored warships were vulnerable to large naval guns, not to experimental explosive devices. Munro's work was filed away in naval archives and largely forgotten. The hollow charge effect was independently rediscovered multiple times over the next 4 decades. In 1910, Egon Neumann in Germany found that a block of TNT with a conical indentation punched a hole through steel plate instead of merely denting it. In the 1920s, Soviet researcher Myron Yakovlevich Sukharevsky conducted similar experiments. In 1936, Professor R.W. Wood at Johns Hopkins University published detailed observations of the phenomenon in the Proceedings of the Royal Society. But it wasn't until the mid-1930s, as Europe began rearming for another world war, that the shaped charge effect attracted serious military attention. The critical breakthrough came from an unlikely source. Henry Hans Mohaupt was a Swiss chemical engineer who had served as a machine gunner in the Swiss army. In his laboratory in Zurich in 1935, Mohaupt was experimenting with methods of propelling metal discs using explosives when he discovered something remarkable. When he placed a steel cone inside a hollowed-out explosive charge and detonated it at some distance from a target, the cone didn't fragment as expected. Instead, it created a narrow, deep hole in the target, much deeper than the diameter of the cone itself. Mohaupt had independently discovered what Munro had observed decades earlier, but with a crucial addition: the metal liner. Where Munro had worked with bare explosive cavities, Mohaupt realized that lining the cavity with metal dramatically amplified the effect. The detonation's pressure wave would collapse the metal liner inward at tremendous velocity, creating a jet of molten metal and explosive gases that could penetrate steel plate far thicker than conventional explosives could affect. By 1937, Mohaupt had refined his invention into a functional anti-tank weapon. He demonstrated it to Swiss military authorities, then to the French, then to the British. The British were skeptical. Hollow charge explosives were already well known, they told him. The addition of a metal liner seemed like an incremental improvement, not worth significant investment. This was a catastrophic miscalculation. The metal liner wasn't incremental, it was transformative. Meanwhile, in Germany, another researcher was making the same discovery. Franz Rudolf Thomanek was a physics student at Vienna's Technische Hochschule in 1932, when he conceived an anti-tank round based on the hollow charge effect. When the Austrian government showed no interest, he moved to Berlin's Technische Hochschule to continue his work under ballistics expert Carl Julius Kranz. On February 4, 1938, Thomanek achieved the same breakthrough as Mohaupt, the shaped charge with a metal liner that could defeat heavy armor. The German military immediately recognized the weapon's potential. By 1940, German forces were using unlined shaped charges to assault fortifications. On May 10, 1940, German airborne troops attacking the Belgian fortress of Eben-Emael used hollow charge explosives developed by Dr. Hürtgen to blast through reinforced concrete emplacements. These early charges lacked metal liners and didn't produce the focused jet effect, but they demonstrated the principle's battlefield utility. By 1941, both Germany and Britain were developing metal-lined shaped charge weapons. Germany produced the Panzerwurfmine anti-tank grenade and began work on larger weapons. Britain developed the No. 68 AT rifle grenade, first issued in 1940, which has some claim to being the first metal-lined shaped charge weapon in combat use. The United States entered this technological race late but with characteristic industrial intensity, when the French communicated Mohaupt's shaped charge technology to the US. Ordnance Department in 1940, he was immediately invited to America. By October 1940, Mohaupt had taken over direction of what would become the Bazooka project. The shaped charge principle that Mohaupt brought to American weapons development was elegant in its physics, but complex in its execution. When a high explosive detonates behind a metal-lined conical cavity, the detonation wave travels through the explosive at speeds approaching 8,000 meters per second. This pressure wave strikes the metal liner, typically made of copper due to its ductility, and collapses it inward. The liner doesn't melt in any conventional sense. Instead, it deforms under pressures exceeding 3 million pounds per square inch, behaving more like a fluid than a solid, despite remaining well below its melting point. The collapsed liner forms into two distinct components. The bulk of the liner material becomes a slower-moving slug, but a portion of the liner, compressed and accelerated by the shaped detonation wave, forms into a high-velocity jet traveling at speeds up to 10,000 meters per second. This jet, though it's often described as molten metal, is actually solid metal deformed into a stream by extreme pressure. When it strikes armor plate, the jet doesn't burn through the steel. It punches through via kinetic energy, the same way a water jet can cut through stone given sufficient pressure. The jet's extreme velocity concentrates enormous energy into a tiny cross-sectional area, allowing it to penetrate steel far thicker than the warhead itself. The penetration depth of a shaped charge is directly proportional to the diameter of the warhead and the quality of the jet formation. A well-designed shaped charge can penetrate armor to a depth of 7 or more times the charge diameter. This is why a relatively small warhead, properly designed, can defeat thick armor plate. The Bazooka's 2.36-inch shaped charge warhead, designated M6, used these principles to achieve theoretical penetration of 3 to 4 inches of armor plate at perpendicular impact. When Lieutenant Colonel Leslie Skinner and Lieutenant Edward Uhl created the first Bazooka prototype in early 1942, they were solving a delivery problem, not an ammunition problem. The M10-shaped charge grenade already existed and worked well in testing. The challenge was getting it close enough to enemy armor to be effective without requiring soldiers to commit suicide in the attempt. Uhl's brilliant insight, spotting that discarded steel tube in a scrap pile at Aberdeen Proving Ground and recognizing it as the perfect launcher, has become legendary. The rocket motor concept came from Robert Goddard's World War I research. The shaped charge warhead came from Mohaupt's Swiss laboratory via the M10 grenade. What made the Bazooka revolutionary wasn't any single technology. It was the integration of existing technologies into a package simple enough for mass production and intuitive enough for rapid training. The weapon that emerged from those hasty 1942 development efforts was crude but functional. A 60-inch steel tube, a wooden shoulder stock, wire sights that were literally bent into shape the morning of the first demonstration, and an electrical firing system using a dry cell battery. The M6 rocket carried a shaped charge warhead containing 8 ounces of pentalite explosive, with a copper liner designed to produce maximum penetration against armor plate. When General Gladion Barnes witnessed that first demonstration at Aberdeen in May 1942, watching Skinner and Uhl hit a moving tank repeatedly with their improvised sights, while 5 sophisticated spigot mortars missed every shot, he immediately ordered 5,000 launchers into production. Not for testing, for combat deployment. The United States was at war, American infantry had no effective anti-tank weapons, and the bazooka looked like the answer to a desperate problem. What nobody knew in May 1942 was that the bazooka had never been properly tested against actual German tank armor under realistic combat conditions. The shaped charge warhead had been tested against steel plate, the launcher had been tested for basic functionality, but the complete weapon system, firing production rockets at actual German Panther, Tiger, or even Panzer IV tanks, accounting for variables like impact angle, armor quality, and fuse reliability, that testing never happened before production began. General Electric delivered the first 5,000 bazookas with 89 minutes to spare before the 30-day deadline expired. American industry had performed a manufacturing miracle, but they had mass-produced a weapon whose real-world effectiveness against modern German armor was about to be discovered through trial by combat. November 8th, 1942. The beaches of North Africa. Operation Torch, the Allied invasion of French North Africa, brought American forces into large-scale combat for the first time in the European theatre. Among the equipment hastily loaded onto transport ships were crates of M1 bazookas, rushed to the invasion forces so quickly that Supreme Commander Dwight Eisenhower was shocked to learn his troops had received no training whatsoever on the new weapon. Soldiers first saw bazookas when crates were pried open on ship decks crossing the Atlantic. No manuals, no instructors, no practice ammunition, just a tube, some rockets, and vague assurances from supply officers that it could stop tanks. The weapon's combat debut was inauspicious. French colonial forces resisted the landings with unexpected intensity. The bazooka saw minimal use during the initial assaults. But as American forces pushed inland and began encountering German reinforcements rushing to Tunisia, the bazooka finally faced its intended targets. The results were catastrophic. The M6 rocket proved horrifically unreliable under field conditions. Primers failed to ignite, fins bent during transport, causing rockets to spiral wildly off course. The electrical firing system corroded in salt air. When rockets did fire and hit their targets, penetration was inconsistent. Some rounds performed as designed, others bounced off without detonating. Still others detonated properly but failed to penetrate armor that testing suggested they should defeat easily. The first documented combat use occurred during the Tunisia campaign in February 1943. The 168th Infantry Regiment of the 34th Infantry Division received bazookas on February 12th, during the Battle of Kasserine Pass. They were learning to use them against German armor attacks on February 14th under the worst possible circumstances, in combat, while being overrun. Corporal James Mitchell, one of the soldiers, issued a bazooka that morning, later recalled the experience in a 1949 interview. They told us it could knock out any tank the Germans had. Point it at the side or rear, pull the trigger, the tank burns. Simple as that. We set up in a wadi about 100 yards from the road, waiting for German armor we knew was coming. When the first Panzer III rolled past, I had a perfect side shot, maybe 60 yards. I pulled the trigger, the rocket hit, and nothing happened. The tank didn't even slow down. We loaded another rocket. This time the primer failed. Dead trigger. The tank spotted us and started traversing its gun. We ran. After months of fighting in Tunisia, American ordnance officers compiled assessments from frontline units. The findings were damning. One American general visiting the Tunisian front could not find any soldiers who could report that the weapon had actually stopped an enemy tank. Not one verified tank kill could be attributed to the bazooka through the entire North African campaign. American soldiers, promised a weapon that would let them fight back against panzers, found themselves as helpless as if they had no anti-tank capability at all. Some units abandoned their bazookas entirely. Others kept them for use against fortifications and infantry positions, where the shaped charge warhead proved effective, but stopped attempting to engage armor. The psychological impact was severe. Troops who had been told the bazooka was a war-winning weapon now viewed it as a dangerous liability that revealed your position without providing meaningful firepower. In May 1943, the Army suspended further deployment of the M1 bazooka. The entire program seemed on the verge of cancellation, but Skinner, Uhl, and the engineers at Aberdeen refused to accept failure. They began systematically addressing each problem. The M6 rocket was completely redesigned as the M6A1. The electrical contact ring system that caused structural weakness in the rocket body was replaced with a wire that unspooled from the rear during flight. Propellant sticks were shortened to reduce peak pressures that could burst the launch tube. The fuse mechanism was improved. Most critically, the shaped charge warhead itself was modified to improve jet formation. The M1 launcher became the M1A1 with simplified construction, better weatherproofing, and improved sights. Weight dropped from 18 pounds to just under 13 pounds. The magneto-firing system replaced the unreliable battery ignition. By summer 1943, an improved weapon and better trained soldiers were ready for a second chance. The testing ground would be Sicily. July 10th, 1943, Operation Husky, the Allied invasion of Sicily. American paratroopers of the 82nd Airborne Division dropped into Sicily carrying M1A1 bazookas into combat. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Unlike the rushed deployment in North Africa, these soldiers had been extensively trained. They understood the weapon's capabilities and, more importantly, its limitations. They knew the bazooka could not penetrate a Panther or Tiger frontally. They knew side shots and rear shots were essential. They had practiced shooting at moving targets. Colonel James Gavin, commanding the 505th Parachute Infantry Regimental Combat Team, and had specifically trained his men with bazookas because they were the only weapons paratroopers could carry that would enable them to engage German armour on reasonable terms. The jump itself was a disaster. High winds scattered paratroopers across 50 miles of Sicilian countryside, but as dawn broke on July 11th, scattered groups of American paratroopers found themselves defending Piazza Ridge against elements of the German Hermann Göring Panzer Division. Tiger tanks from a company of the 215th Tank Battalion, along with Panzer IV medium tanks, approximately 700 infantry, and one armoured artillery battalion, advanced toward American positions. The paratroopers were outnumbered, outgunned, scattered, and facing 60-ton Tiger tanks whose armour they had been specifically warned was too thick for frontal bazooka engagement. What happened next became part of 82nd Airborne legend. When the first Tigers advanced up the ridge, American bazooka teams held their fire. Seasoned NCOs, remembering the failures in North Africa, enforced fire discipline. Wait for side shots, wait for rear shots. Don't waste ammunition on frontal armour. As Tigers manoeuvred to bring their 88mm main guns to bear, exposing their flanks as they traversed the rough terrain, bazooka teams opened fire. The improved M6A1 rockets performed dramatically better than the original M6 had in Tunisia. Rounds that hit Tiger side armour at proper angles penetrated. When they penetrated, they often ignited ammunition or fuel, causing catastrophic secondary explosions. But Gavin's after-action report also documented the weapon's limitations with brutal honesty. Bazooka rounds fired at Tiger frontal armour simply bounced off. The shaped charge warheads couldn't penetrate the Tiger's thick frontal plates at any range. Crews that attempted frontal shots often died moments later when Tiger main guns returned fire. The battle raged all day. Naval gunfire from destroyers proved decisive. Sherman tanks arrived as reinforcements. By evening, the German attack had stalled. The Hermann Göring Division withdrew, having suffered significant losses. After-action reports credited the M1A1 bazooka with proving effective when properly employed by trained soldiers against appropriate targets. The weapon had vindicated itself in Sicily, but only because American soldiers had learned through bitter experience what targets they could and could not engage. This lesson, that the bazooka required specific tactics and careful target selection to be effective, should have been obvious from basic physics. The M6A3 rocket, the final wartime production version with improved shaped charge standoff and better fusing, could penetrate 3.5 to 4 inches, roughly 89 to 102 millimeters, of armor plate when striking at perpendicular angles. This performance was adequate against most German light and medium tanks from the side or rear. A Panzer III had 50mm side armor. A Panzer IV had 30mm side armor and 20mm rear armor. Assault guns like the Stooge 3 had similar protection. Even from less than ideal angles, a properly functioning bazooka rocket could defeat these vehicles. But the Panther was a different proposition entirely. The Panther's side armor measured 40mm, theoretically within the bazooka's penetration capability. But that 40mm was high-quality face-hardened steel specifically designed to resist shaped charge attack. The armor plates used an interlocking tenon joint arrangement that gave the welds added strength. More critically, the Panther's designers had angled even the side armor slightly and had positioned external equipment, fuel tanks, and other components to create effective spacing that degraded shaped charge jet formation. When a bazooka rocket struck a Panther's side armor at optimal perpendicular angle, At close range, with a properly functioning warhead, penetration was possible. American combat reports documented such kills, but achieving all those conditions simultaneously in actual combat proved extraordinarily difficult. A Panther moving at speed presented a brief target window, firing from ambush. Positions in hedgerows or buildings, American bazooka teams often had to shoot through vegetation or debris that could detonate the rocket prematurely before the shaped charge standoff distance was correct. Impact angles were rarely perpendicular. A Panther moving at even a slight angle to the firing position could present side armor at 30 or 40 degrees off perpendicular, dramatically reducing penetration probability. Most damagingly, the Panther's tactical employment emphasized presenting frontal armor toward threats whenever possible. German tank commanders were trained to keep their glacis plate oriented toward known or suspected enemy positions. The Panther's frontal armor, an 80mm plate sloped at 55 degrees, created effective thickness of approximately 140 millimeters. No bazooka in American service could penetrate that protection. The only reliably vulnerable frontal area was the gun mantlet, a curved 100mm thick cast steel housing protecting the 75mm main gun's mounting. Even there, penetration required hits at near perpendicular angles and close range, typically under 100 yards. At 100 yards, a Panther's coaxial machine gun could shred a bazooka team in seconds. The 75mm main gun could destroy any cover the team might be hiding behind. The tactical mathematics were brutally simple. To kill a Panther with a bazooka, you needed to get close enough that the Panther could easily kill you first, identify and exploit a brief vulnerable moment when side or rear armor was exposed, and achieve penetration with a single shot because you likely wouldn't survive to fire a second time. This is the reality that Private First Class Thomas Harmon encountered in the Hürtgen forest in November 1944. He had done everything right. He had achieved a side hit at proper range, but the Panther's armor quality, the slight angle of the hull, perhaps a rocket that had absorbed too much moisture during weeks in muddy German forests, or a dozen other variables that could degrade shaped charge performance, meant that perfect execution still resulted in failure. The bazooka hadn't failed because of poor design. It had encountered an opponent that exceeded its design parameters. What makes this story particularly bitter is that American ordnance engineers knew about the Panther problem months before soldiers like Harmon faced it in combat. The Germans had introduced the Panther at the Battle of Kursk in July 1943. By early 1944, American intelligence had obtained detailed specifications of Panther armor. Engineers at Aberdeen Proving Ground had access to captured Panthers for testing. The tests were conducted. The results were definitive. The 2.36-inch bazooka could not reliably penetrate Panther frontal armor. Side armor penetration was marginal, highly dependent on impact angle and range. Rear shots offered better odds but still weren't guaranteed. The obvious solution was a larger warhead. During U.S. trials of the M1 bazooka in 1942, ordnance officers had proposed increasing the warhead diameter to improve penetration. Those proposals were rejected on grounds of weight, production complexity, and the assessment that the 2.36-inch diameter was adequate for expected threats. By 1944, that assessment was clearly wrong, but American production was fully committed to the 2.36-inch system. Hundreds of thousands of launchers had been manufactured, millions of rockets were in the supply chain. Changing to a larger diameter would require retooling factories, retraining soldiers, and accepting months of disrupted supply while the transition occurred. More critically, American commanders in the field desperately needed bazookas right now, even marginally effective ones, more than they needed theoretically superior weapons that might arrive months in the future. So the 2.36-inch bazooka remained in production and continued shipping to Europe, despite everyone involved knowing it was inadequate against Germany's most modern armor. Soldiers weren't officially told about these limitations. Training materials continued, emphasizing the bazooka's effectiveness against tanks generally, without detailed breakdowns of which specific German vehicles it could and couldn't defeat reliably. This wasn't malicious deception. Military leaders genuinely believed that telling soldiers their primary anti-tank weapon couldn't defeat the enemy's best tanks would destroy morale and tactical initiative. Better to let soldiers believe the weapon worked and trust their tactical skills and combined arms support to make up the difference. This calculus led directly to moments like Harmon's experience. A soldier who believed his weapon would work, who took a perfect shot and watched it fail, now had to process that failure while under fire from a tank that thought it was invincible because the American infantry had just proved they couldn't hurt it. The German perspective offers illuminating counterpoint. By mid-1944, German tank crews had experienced enough bazooka engagements to develop tactical responses. Intelligence reports compiled from interrogations of captured American soldiers revealed the bazooka's specifications. German ordnance experts examined captured launchers and rockets in detail. Their assessment was more accurate than American training materials. The bazooka was dangerous to light armor and older tanks. Against Panthers and Tigers, it required very specific circumstances to be effective. Front armor was essentially immune. Side armor was resistant except at close range and perpendicular impact. Rear armor was vulnerable, particularly the engine compartment, but rear shots required American teams to survive long enough to maneuver into position, which German combined arms tactics specifically prevented. German tactical doctrine emphasized keeping infantry close to tanks specifically to suppress enemy bazooka teams before they could achieve favorable firing positions. Panther commanders were trained to present frontal armor toward threats, maneuver constantly to prevent enemy infantry from working around to the sides, and use coaxial machine guns aggressively against suspected bazooka positions. When Panthers did encounter bazookas in favorable circumstances, when American teams achieved surprise side shots at close range, the results could be lethal. But the Germans calculated, correctly, that their tactical countermeasures would prevent most such occurrences. The Panthers' real vulnerability wasn't to American bazookas, it was to American combined arms coordination. When bazookas were employed as part of integrated tactics, with artillery suppressing German infantry, air support disrupting German maneuver, and tank destroyers, or Sherman tanks, providing overwatch, while bazooka teams maneuvered into ambush positions, the Panthers' advantages evaporated. But that coordination required radios, forward observers, air superiority, and tactical patience that frontline infantry fighting in forests or hedgerows rarely possessed. September 20th, 1944, the Battle of Aracourt in eastern France. Lieutenant Colonel Charles M. Carpenter, flying his L-4 Grasshopper observation plane nicknamed Rosie the Rocketer, approached German armored positions with 6 M9 bazookas mounted on his wing struts. Carpenter had modified his aircraft through months of experimentation, installing an electrical firing system that let him launch rockets while flying. His attack profile involved diving from altitude to approximately 100 meters above target, firing rockets, then pulling up steeply to escape return fire. The tactic exploited the Panther's critical vulnerability. Top armor. While Panther frontal armor measured 80 mm and side armor 40 mm, the engine deck and turret top armor measured only 16 to 25 mm. Carpenter's diving attack meant his rockets struck top surfaces at steep angles, against armor that even the 2.36-inch bazooka could penetrate reliably. During the Battle of Aracourt, Carpenter was credited with destroying 6 German armored vehicles, including 2 Panthers. Witness accounts claim higher numbers, but official records list 6 confirmed kills. The success wasn't due to any special capability of the bazooka itself. It was due to Carpenter finding a way to attack the one part of the Panther that the bazooka could actually defeat. This pattern repeats throughout the American bazooka's combat history. When soldiers could achieve proper angles against vulnerable armor, the weapon performed adequately. When they couldn't, it failed. The shaped charge principle was sound, the physics worked. But physics, operating in a vacuum, differs dramatically from physics operating in combat, where the enemy's armor is specifically designed to defeat your weapon and the enemy's tactics specifically prevent you from achieving favorable firing positions. By January 1945, American forces were fighting through Germany itself. The Battle of the Bulge in December had demonstrated once again the bazooka's limitations and possibilities. American infantry, caught off guard by the German offensive, relied heavily on bazookas to defend against Panther and Tiger attacks through the Ardennes. The weapon's performance was mixed. Some units reported excellent results, others reported complete failure. The difference usually came down to training, tactical employment, and luck. One of the war's most remarkable bazooka engagements occurred on January 4, 1945, during Operation Nordwind, Germany's last major offensive in the West. Near Rimling, France, in Alsace, an American bazooka team engaged a Jagdtiger heavy tank destroyer. The Jagdtiger was the most heavily armoured fighting vehicle in World War II, with 250 mm of frontal armour that was practically invulnerable to any anti-tank weapon in Allied service. The bazooka team managed to position themselves for a shot at the Jagdtiger's thinner side armour, scoring a direct hit on the ammunition bustle. The shaped charge penetrated the 80 mm side plate and detonated stored ammunition, causing a catastrophic kill that destroyed the vehicle and killed the entire crew. This engagement shows that when correctly aimed at vulnerable points, the bazooka could still be effective against even the best protected of armoured vehicles, though it required significant skill and more than a little luck to accomplish. But for every success story like the Jagdtiger kill, there were dozens of failures. Bazookas that misfired, rockets that bounced off, teams that were killed before they could shoot. The weapon that had been described as revolutionary in 1942 looked increasingly inadequate by 1945. American ordnance engineers weren't blind to these problems. By late 1944, work had begun on a completely redesigned weapon, the M20 Super Bazooka. The new weapon featured an 88.9 mm, 3.5-inch diameter, matching the German Panzerschreck that had itself been copied from captured American bazookas. The M28 A2 rocket could penetrate 11 inches, 280 mm, of armour, nearly double the original bazooka's capability. But development came too late. The war in Europe ended in May 1945 before the M20 could be deployed. In the Pacific, where Japanese tanks were lighter and the fighting focused more on fortifications, the original 2.36-inch bazooka remained adequate through Japan's surrender in August. The bazooka's true vindication, or perhaps its final condemnation, came 5 years later in Korea, when North Korean forces equipped with Soviet-supplied T-3485 tanks crossed the 38th parallel on June 25, 1950, American forces in South Korea possessed 1958 M9A1 bazookas as their primary anti-tank weapons. The T-3485's frontal armour measured 90 to 100 mm. On July 5, 1950, Task Force Smith, consisting of 406 U.S. soldiers, faced approximately 5,000 North Koreans, supported by 33 T-34 tanks. Armed with 6 M9A1 bazookas, they fired 22 rockets with zero effect. The rockets literally bounced off the T-34's armour. The task force was routed. Colonel Robert Martin of the 24th Infantry Division was killed on July 8, attempting to stop a T-34 with a 2.36-inch bazooka. The weapon that had struggled against Panthers in Europe was completely ineffective against the T-34. General Douglas MacArthur immediately requested emergency shipment of M20 Super Bazookas. Rock Island Arsenal shipped the first M20s to Korea, accompanied by instructors from Fort Benning. The first combat use occurred on July 20th at the Battle of Daejeon. The results were immediate and dramatic. The M20 was credited with destroying 8 T-34 tanks on its first day of combat use. Major General William F. Dean personally used the M20 against T-34 seconds during the battle, engaging a T-34 from a second-story window at less than 10 yards range. He hit the turret ring, set the tank on fire, and killed the crew. Korea proved what American ordnance engineers had known since 1944. The 2.36-inch bazooka was fundamentally inadequate against modern armour. The shaped charge principle was sound, but the diameter was too small. The German response offers the final irony. When German forces captured American bazookas in late 1942, their ordnance experts immediately recognized both the weapon's potential and its limitations. The solution was obvious: make it bigger. The Raketenpanzerbüchse 54, nicknamed Panzerschreck, was essentially a scaled-up bazooka. Germans increased the warhead diameter from 60 mm to 88 mm, enabling penetration of 160 to 230 mm, roughly double the American capability. But the Panzerschreck weighed 24 pounds compared to the M9A1's 13 pounds. Its rockets continued burning for 2 meters after leaving the muzzle, creating enormous backblast that required protective equipment. German soldiers had to wear ponchos, heavy gloves, and gas masks. The massive smoke cloud revealed shooter positions instantly. Approximately 300,000 Panzerschrecks were produced compared to 476,000 American bazookas. Germany's disrupted industrial capacity couldn't match American production even when German weapons were technically superior. This pattern defined the war. Germany developed sophisticated weapons. America produced adequate weapons in overwhelming numbers. But adequate wasn't enough against Panthers. By late 1944, American ordnance engineers had begun work on the M20 Super Bazooka, featuring an 88.9 mm diameter matching the Panzerschreck. The M28A2 rocket could penetrate 11 inches, 280 mm, nearly double the original capability. Development came too late. The European War ended in May 1945 before the M20 deployed. The weapon's vindication came 5 years later in Korea, when North Korean T-3485 tanks crossed the 38th parallel on June 25, 1950. American forces possessed M9A1 bazookas as their primary anti-tank weapons. On July 5, Task Force Smith fired 22 rockets at T-34 seconds with zero effect. The rounds bounced off. Colonel Robert Martin was killed on July 8 attempting to stop a T-34 with a 2.36-inch bazooka. General MacArthur immediately requested M20 super bazookas. On July 20 at Daejeon, the M20 destroyed 8 T-34 seconds on its first day of combat. The weapon American infantry needed in 1944 arrived in 1950. The men who designed the bazooka weren't responsible for its inadequacy against Panthers. Leslie Skinner and Edward Uhl created exactly what was requested in 1942, a launcher that could defeat contemporary German armor. That it couldn't defeat armor introduced 2 years later reflected accelerating technological change, not engineering failure. Nobody had anticipated the Panther. Henry Mohaupt's shaped charge principle was revolutionary. The science was sound, but science operates within constraints of production capacity, logistics, and battlefield conditions. The real lesson isn't about shaped charges or armor penetration. It's about the gap between what weapons are designed to do and what they're asked to do in combat. The bazooka was designed to defeat 1942 German armor. It did that acceptably. When asked to defeat 1944 armor, it struggled, not because it had changed, but because the enemy evolved faster than American industry could respond. Private First Class Thomas Harmon survived the war. In a 1986 interview, he reflected on that moment in Hürtgen forest. We were told the bazooka could stop any tank. After watching that Panther shrug off a perfect side hit, I never quite believed anything the army told us about equipment again, but we kept using bazookas because what else did we have? You learn its limits and work within them. Most of us survived by learning when not to shoot, when to let the tank pass and call in artillery. The guys who died were usually the ones who still believed the training manuals. That bitter wisdom defined the late-war infantry experience. The bazooka had given soldiers the ability to fight back against armor, revolutionary in 1942. But by 1944, fighting back wasn't the same as winning. The shaped charge principle that Charles Munro discovered in 1888, that Mohaupt weaponized in the 30s, that Skinner and Uhl turned into the bazooka in 42, transformed infantry anti-tank warfare permanently. The fact that the first implementation couldn't defeat every enemy tank doesn't diminish that transformation. It simply reminds us that technology evolves, enemies adapt, and the weapon that seems revolutionary today becomes inadequate tomorrow. The soldiers who carried bazookas against Panthers weren't using revolutionary weapons. They were using yesterday's answer to today's problem. That they found ways to make it work anyway is testament to their skill, their courage, and their refusal to accept that inadequate weapons meant inevitable defeat. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.